Welcome to the microwave communication course. Now we see here today we start with this new model or new concept of a microwave waveguide and a component there. As we have seen earlier that a microwave fundamentals and some field theory component that we have seen, and you know that the basic microwave frequency range, as we say that it is in terms of a gigahertz. That's why microwave is nothing but a small wave. So now we say that a small wave is to be propagating through the guide. The wave is propagating by a mechanism, that is a guiding mechanism, and that guiding mechanism is called as a waveguide. If your wave is propagating, this one is about a wave is propagating. This what which wave? That is about a small wave. It will be propagating through some mechanism that is about a structure. So that is about a guide that guiding the wave to be propagating in a space. So that's called as a waveguide. Now, what is the waveguide structure? Okay, so we talk here about that micro waveguide and its components, and we will see that what are the various waveguides are there, and then that waveguide related components that we will learn here. So basic, there are the two types of a waveguide. One is about a rectangular waveguide and a circular waveguide. These two waveguides are used. So mostly, if you see that in application, so rectangular waveguide is used. The word is a rectangular waveguide because that waveguide structure is of a rectangle one. It is about a hollow metallic tube with rectangular cross section. So how your waveguide looks like? So simply I draw here that a rectangular waveguide, and then we'll talk about their characteristics of a waveguide. Then we'll talk about advantages and disadvantages of this waveguide. First of all, we'll go through the rectangular waveguide. Now this is about a rectangle. This one is about a cross section of a waveguide. Now you can see that this one is about your rectangular waveguide. It is about a hollow tube. Okay, this one is about a rectangular cross section. If you cut this here, you will get that a rectangular cross section. This one is about your rectangular waveguide. Now your wave is propagating through this guide. Okay, that is wave is propagating through this rectangular waveguide. So that's why we can say that word. We say that this rectangular waveguide is nothing but what? It is a hollow metallic tube. Okay, it is about metallic one, hollow metallic tube with a rectangular cross section. And if you see that internally, that walls of this rectangular waveguide, if you see that internally, that walls are conducting walls. Outside, it is to be seen as a metallic one, but internal structure, it has a internally conducting wall. This, if you if you see the cross section there of this particular waveguide, it is internally for this particular tube. This one is about a conducting one. These walls of this waveguide are a conducting one, and wave is propagating through this. Similarly, here we can say that your wave is propagating through the rectangular waveguide. So similarly here, the section, if you cut the section here, likewise, so your wave will be propagating through the guide. So we say that input here, and we'll get that a output here. Now we see that, okay. Now we talk about that how your wave is propagating through this guide. Now since this internal wall is a conducting one, the wave propagating through this guide are due to the total reflection. Which wave will reach to these conducting walls here at one side, here another side. So means your wave is reflecting from this conducting wall, and through the reflection, wave is propagating inside this rectangular waveguide. Okay, these waves are propagating through the, what is the wave? It will propagating through the a conducting wall. Okay, so now we see here how your wave is propagating. We say that the wave is propagating through this guide, that is about through this reflection phenomena of a reflection. Now, because due to the particular phenomena of a reflection, so wave propagating through the waveguide, it has a various mode. Means various modes are existing in the waveguide. So what are those various modes? Various modes are nothing but what? If you consider the example of a transmission line, in a transmission line, if you consider that it is a two-wire line, and through this two-wire line, your wave is propagating. Okay, through this two-wire line, wave is propagating. But if you consider that at this particular two ends, what will happen? The wave we are getting through this particular wave, it is only with the, what you can say, that only in a one direction there. But our aim is about that wave is to be propagating in the all the direction. Okay, it is to be propagating in the all the direction. So there is no limitations about that wave. It is to be propagating in which direction? It is to be propagating in the all the direction. So now we will see here what is the difference between that rectangular waveguide and this difference between this coaxial cable or a two wire line. Now in a transmission line, wave is propagating through the wire. Signal is propagating through the wire in terms of a, what you can say, that electrical signal. Even if you consider that a coaxial cable, wave is propagating, your signal is propagating through this coaxial cable. That is nothing but a two wire line. Okay. Now, but in the case of a rectangular waveguide, so signal propagating through this rectangular waveguide in the form of a wave. Okay, it is propagating in the form of a wave. Instead of a signal current, it is propagating here in the form of a wave. So now, why these waveguides are used over this transmission line? If you see the example that of a transmission line, so what happened to the transmission line or a two-wire line or a coaxial cable? So signal of a high frequency could not propagating through this transmission line or a two-wire line or a coaxial cable. So now, why we could not propagating the high frequency signal through this coaxial cable? Because if the signal frequency is high, then coaxial cable or a coaxial wire will act as a antenna. At a high frequency, that wire will act as an antenna, so it radiates a signal in a space. So that's why two wire line or a coaxial wire not used at a microwave frequency, because wave will be, when we propagate the wave through this wire or a transmission line, then that wave will propagate in a space because of that irradiation at a high frequency. But in the case of a rectangular waveguide, it will support a high frequency signal. That rectangular waveguide is nothing but a transmission line or a transmission medium in a microwave. Okay, that is about a waveguide. It is to be considered as the one transmission medium. But in the case of a wire, so it will just propagating the low frequency signal, not a high frequency signal. But rectangular waveguide will support a high frequency signal there. Now the structure is just like a hollow metallic rectangular or a hollow metallic circular one. So this is what about a rectangular waveguide. Now if you see that a circular waveguide is just like a hollow pipe or a circular pipe you're supposed to be considered. It is just like a circular pipe. Okay. And then inner wall of that circle or inner wall of this rectangle is made up of a conducting material. And this type of a waveguide or this type of a tubes, that rectangular or a circular tube, that is to be used to transmit the wave. And this rectangular structure or a circular structure will guide the wave to propagate from one place to the another place. So that's why it is called as a wave guide. And the shape is about whether it is a rectangular shape or a circular shape. So according to that, it has the types of a waveguide, that is rectangular waveguide or a circular waveguide. Now, when we say that we are propagating through the guide, so that is about what, whichever the plane waves are there that is propagating through the guide, that is because of that reflection. Means your waves are reflected from the wall here. So internally, if you see that when it reaches here to the wall, so it will be reflecting from this wall. When it reaches here, it will be again reflecting. Means your waves are reflecting from this internal walls of the waveguide. So that's why when we say that waves are reflecting from this walls, so then it has a component, okay, that it has a two component, that is about a either electric field component or a magnetic field component, and that these components are in the direction of propagation of the wave. Okay, means what we can say here, I am saying that this is about a direction of propagation. Direction of propagation is supposed to be a z now. So then it has either z component, ez component, or it has a sz component. Means either it has a electric field component or a magnetic field component in the direction of a propagation of a wave. Means we can say that the wave propagating through this particular guide, it is not a transverse electromagnetic wave. What is the TEM wave? TEM wave means what? Because TEM wave is propagating through the wire. TEM wave means what? It doesn't have any component that is propagating through this direction of the propagation of wave. Means we can say that Ez is equal to Sz is equal to 0. Okay, it is about a 0. That is about a TEM wave. Okay, but in the case of a waveguide, either Ez or a Sz component is present, and that component is propagating, or it is what we can say that that component is propagating toward the along with the direction of propagation of a wave. So what is the direction of propagation of wave? It is about the z. So in the case of a rectangular waveguide, either Ez or Sz component is propagating along with the direction of propagation of wave. So based on that, whether it is Ez component is present or Sz component is present, according to that, there are the two types of a propagation, that we can say that uh, two types of a propagation here. We can say that modes, we can say that modes exist. It is mode is about a T mode or a TM mode. Means your wave is propagating, either it has a T mode of a propagation or it has a TM mode of a propagation. So what do you mean by this T mode of a propagation and a TM mode of a propagation? Okay, so we'll see in detail. So before that, we should know that what is the reflection, how your signals are reflected from this particular uh, from this internal walls of this waveguide here. How your signals are reflecting here. So your signals are reflecting through the walls of this rectangular waveguide. So it has what two components. One is about a normal component and one is about a parallel component. So parallel component and normal component, just like if we consider that we say this about your rectangular waveguide, and we can say that your wave is propagating through this guide. Suppose we consider this about the direction of wave component here. This one is about the direction of wave component here, and we can say that we have the black one. Means your signal is propagating through this way here. That is, this one is nothing but your signal. Okay, that is propagating here. So it has a two components. So that what you can say that your signal is propagating, that is about a lambda. When it will reach at this particular wall here, so it will be reflecting. Okay, so this one is about what you can say that at this particular place, it will reach, then it will be reflected back. So it will reach again, it will be reflected back. So this particular vector, it has a two component. It has one vertical component, it has a parallel component. That's why this particular component supposed to be, we say that it is a normal component along with. Okay, so this one we supposed to be consider that for this guide, it has a lambda normal here, and through this there will be a lambda p. That we can say that that is about the component in the direction normal to the reflecting plane, and another component that is about a parallel to this particular plane. If we can say that a plane wave is propagating through the guide, then there will be reflection in the waveguide, and that reflection it has a normal component in the direction normal to this reflecting plane, and a parallel component, okay, that is to this parallel to this plane here. So that is about what we can say that a component, normal component, and a parallel component. So now from this we can calculate that this is theta. So we can find out what will be the normal component value. We can talk about that normal component value. Lambda n here is equal to lambda by cos of theta adjacent to the theta. And parallel component is this one here. So that's why parallel is nothing but what is sine of this one, sine of theta. And that theta is nothing but what a angle of incidence at this particular. This is about your lambda component. This one is about the angle of incidence, and this lambda is nothing but what, that is about the wavelength of that signal that is propagating through this medium, through this rectangular waveguide. Okay, that is about a lambda component. So that's what we can say that a rectangular waveguide, and these are nothing but the normal component, and we can say that uh, parallel component in this guide here. Okay, in this rectangular. Now, at what frequency these rectangular waveguides are used? Generally, the rectangular waveguides are designed, or we can say that it is to be operate at a different frequencies there. But in our laboratories, okay, in our lab, so we have the rectangular waveguides that are operating at a x band of a frequency. That is about a x band of a frequency. So what will be this band, x band? What is the range of this frequency in this x band? So generally, we can say that x band start from what, 8 gigahertz to a 12 gigahertz. This one is about the band of a frequency. And in a lab, generally standard waveguides are used. So generally, that standard waveguide or that standard is nothing but what, a WR90 standard that is used in the laboratory here, and that WR90 standard. So it has dimensions specified, because dimensions of this rectangular waveguide. It is depending upon that operating frequency of this waveguide, or a cutoff frequency, you can say. So we will see that how to calculate that a cutoff frequency of this rectangular waveguide. Okay. Now, generally, if you consider that a rectangular waveguide, so it has some thickness here. Okay, it has some thickness. So similarly here it has some thickness. Likewise, we say it has some particular thickness. It has some particular thickness. So that is about the thickness. We can say a thickness here. But from this particular place, from the internal side, okay, this is about the internal length, or we can say that inner width or inner height. This is about the inner height or a inner width. So what will be the inner width and a we can say that inner height of this rectangular waveguide. So for this rectangular waveguide, we say that this one, this particular thing is nothing but what we can say. It is about the width. This is about the width of this rectangular waveguide. And this one is nothing but what? A height. Okay, this one is nothing but a height here. And from this to this is nothing but what? A length. This one is about the length of the waveguide. So that length of the waveguide, it is depending upon the application. So how long we can use this particular length of the guide. So according to that length is depend. But your parameters totally depending upon that height and width of this waveguide. So it has a two width. We can say inner width and outer width. Okay. So inner size of this waveguide and a outer size of this waveguide. That okay. Along with the thickness, then outer width. Okay. Without thickness, that is about the inner width. So for this WR90 standard, okay, so we can say that the inner width is nothing but, okay, so we can say that WR90 standard, we can talk about that inner width. So inner width is equal to how much? Inner width is about a 2.286 centimeter. Okay, this is about the inner width, 2.286 centimeter. Or we can say that it is in terms of what? A point 0.9 inch, or you can say that a point 0.9 inch here. And then we can say that a outer width is equal to, or sorry, we will not talk about that outer width. We are just interested in the inner width there. Okay, you can say that will not talk. It is depending upon that for this different standard, so different make outer width may change, but inner width for WR90 it is same. Okay, but outer width depending upon that, okay, that particular manufacturers or all. Okay, so but inner width is fixed. So we'll talk about that inner width. So inner height. Inner height is equal to 1.016 centimeter. Inner height is equal to 1.016 centimeter, or we can say that 8.4 inch here. And if we see the outside dimension for the WR90 standard, okay, so this is about the inner one. So if we talk about that outer dimensions are nothing but what? We'll talk about that outer width now. So outer width or outer dimensions are nothing but a 2.54 centimeter or 1 inch, and we'll see that the height, outer height is equal to 1.016 centimeter, or we can say that is about a approximately it is about a zero point 0.5 inch. Sorry, this one is about a 1.27 centimeter and a zero point 0.5. That is about your dimension. And we say that it has a electric field component and a magnetic field component. So both are there that are propagating through this waveguide there. So we say that when the both the components are present, means your all the field components are confined in a waveguide. Therefore, the waveguide has a no power loss. And since that waveguide has the inner conductor, okay, walls of these waveguides are conducting one. So because of that, a that walls are conducting there, so that's why it doesn't have a dielectric loss. So dielectric loss is negligible. Okay, so that's about your waveguide. And we can say that it has a various modes of a propagation, and that various modes of a propagation, it is depending upon that what will be the waveguide and which band we are using there. So that is about, you can say that, a waveguide and their components. So now we talk about that what are the advantages of this waveguide, and generally we can say that it is about the X band of your operation, that is about the 8 to 12 gigahertz of frequency. So for every waveguide, so it has some fixed cutoff frequency for a given particular mode. So what are the modes? We talk about in detail, that is about the mode, T mode and TM modes of a propagation there. And then we'll talk about that what are the various modes of a propagation and what will be the cutoff frequency. Cutoff frequency for this mode, it is depending upon that operating wavelength of this waveguide and what will be the modes of the propagation there. What type of mode, either it is a T mode or a TM mode of a propagation there. So according to that, we will see that what will be the modes and what are the cutoff frequency for the given particular mode. So all the time we should know that what are the dimensions of the waveguide. And then we can see that for the given particular waveguide, so based on this particular dimensions, so we can find out what will be the modes of propagation, what are the uh, other parameters of the waveguide. So then advantages of rectangular waveguide. Advantages of rectangular waveguide. Okay, so some people say that RW, okay, RWG likewise. So just we'll talk about that rectangular waveguide and about what are the advantages of this rectangular waveguide. The first advantages we say that earlier, because we have a power losses are low there. Why power losses are low? Because it has a internal walls are conducting one. Because of that internal wall, that length of the waveguide is large. So that's why, so we can say that it has a large surface area, and because of that large surface area, then it reduces that a copper losses. That is about the I square R losses. So we can say that one is about a loss, okay, that is about a copper loss. So that is about a, it has a copper loss, that is copper loss is a low one, or it will reduces because of that a large surface area. Okay, so because of that large surface area, so it will reduces that a copper loss, that is called as a I square R loss. If we consider that the surface area of that wire, that we can say that a coaxial cable, so if we consider that it is a large because it has the outer surface area. So as compared to this waveguide, okay, so we can say that at a micro frequencies, so that wave is propagating through the conducting walls of the waveguide there. So it is to be considered that a small layer is to be used for wave propagation there. So that's why it reduces the losses there. Then another loss is about a dielectric loss. Now in the case of a dielectric loss, if you compare with a transmission line or a two-wire line, or if you compare with a coaxial line, coaxial cable, because at a micro frequencies, if you consider that these wires are get heated. Okay, means even in general we talk about that any signal is propagating through this. So we can say that generally a dielectric loss occurs because of that heating uh, inside that particular wire. Okay, so but in the case of a waveguide, so dielectric medium is a air because it is about a hollow tube. So medium is a dielectric medium is nothing but what? Air. So because of that air, so it has a low dielectric loss. Dielectric losses are low, but in the case of a wire, so it has a uh, dielectric losses are large because of that. Why it is large? Because two wires are there, and in between that two wires, the insulations are used, and that insulations get heated. Okay, because of that heating of the insulation between the two wires or between that conductor, so it has a dielectric loss. Dielectric loss occurs due to the heating of the insulation. But in the case of a waveguide, that inner wall is that hollow tube is there, and because of that hollow tube, that it has a air internally, inside it has a air there. So dielectric medium or dielectric in a waveguide is the air, and because of that, it has a lower dielectric losses as compared to the coaxial wire or a what you can say that a two wire line. So that's why dielectric losses we say that a low here. Then a power handling capability. Okay. Now the power handling capability. So is if you consider that a waveguide, so waveguide it has we say that internal structure is about it has the inner conducting surfaces there. But if you can compare with the a coaxial wire, okay, or a you can say that the two wire line. So waveguide handle a more power than the coaxial line. Okay, why? Why it is just if you see that so talk about that if you see the structure of this a two wire line or a coaxial cable, so that wire has a that I supposed to be draw here the cable now. Now this is about a circular wire now. Okay, coaxial cable. So in a coaxial cable, it has a inner conductor, and it this one is about a outer conductor. Okay, inner conductor and outer conductor. Now the because the distance between this inner conductor and outer conductor is small here, and because of that small distance, so power handling capability of this wire reduces. If you consider the rectangular waveguide or a circular waveguide, now I have just consider the circular waveguide now. Distance between this conductor here, okay, internal wall we say, it is about a large. Okay, so that's why the waveguide handle more power than the coaxial cable because the distance between the conductor in a coaxial cable is small, but distance between the conductor, even if you consider the rectangular waveguide, it is a large. So because of that, so power handling capability of this waveguide is a large. So these are about the advantages of a rectangular waveguide. Similarly, the advantages it has some disadvantages there. Okay, so waveguide it has disadvantages. So what are the disadvantages? The rectangular waveguide, if you see that physical size of this rectangular waveguide it is the large, okay, size. So that is about, one is about, we can say that physical size as compared to the coaxial wire or a coaxial cable, so that it has a size is a large. So that's why we can say that because of that size, so that is used in the waveguide, that is used in the application. So it has the limitations for this, for installing or for utilizing at a different frequency there. Then another is about what? Because we can say that a rectangular waveguide is about a hollow tube, we say, hollow pipe shape, and it is heavy one. And because of that, it is difficult to install. Okay, installation of this rectangular waveguide, so it is difficult to install. And again, if because of that, if we can say that a hollow tubes and everything is there, so that weight of this particular rectangular waveguide as compared to the coaxial cable is a larger. That is about, we can say, uh, that disadvantages of this rectangular waveguide. Now we'll talk about that, some facts about the waveguide, and then we talk about that how your rectangular waveguides are used. Facts about it. As we have mentioned that earlier, that is about what are the characteristics or some facts about the waveguide. Generally, we say that in a two-wire line or a uh, coaxial cable, so that propagation is nothing but what? If you consider that in the form of a current or a voltage. But in the case of a waveguide, it is propagating in the form of a wave there. Wave is propagating. Here it is, wave is propagating, but in the case of a coaxial cable or a wire, it just use a current or a voltage. Means your signal is propagating in the form of a current or a voltage there. Means we talk about that electric field and a magnetic field component that can be obtained based on this current and voltage. But here in the case here wave, it has a, we can find out directly the what will be the current and voltage there. Then that dimensions of the waveguide, the size, it is totally depending upon that what will be the wavelength or operating wavelength of this particular waveguide. So dimensions totally depending upon that wavelength. Waveguide dimensions are depending upon that wavelength. Means we can say that it is totally depending upon that lambda. Okay, what is the operating wavelength of this waveguide? So according to that, size of that waveguide will be changes here. Now we say that if waveguide is used at a high frequency. Okay, waveguide is used at a high frequency. Because of that high frequency, we say that waveguide means wave is propagating through the waveguide. It is nothing but only the high frequency. Low frequency signal could not propagating through the waveguide. So that's why the waveguide is called as a high pass filter. It is to be operating at a high frequency. So that's why you can say that it is called as a high pass filter here. Okay. High pass filter means what? From this gigahertz of a range. Okay. Means it will operate only at the higher frequency there. So that's why you can say that about it is that waveguide is act as a high pass filter there. And their waves are propagating through this waveguide. It has a different modes. Okay, and that different modes can be separated based on the frequency there. Okay, different modes can be propagating. So that different modes are propagating there through this waveguide, they are separating based on the whatever the frequency there. And as we talk about that, it has a large handling capability of a large power handling capability as compared to the coaxial cable, and that waves are propagating through this waveguide by the reflection from the walls. Okay, so means it is means your signals are propagating through the reflections there. As if we compare with the coaxial cable, the wave is propagating, the signal is propagating through this conducting wire. Okay, so because of that signal propagating through the conducting wire, so losses are more. But in the case of a waveguide, waves are propagating through the reflection from the conducting walls, and because of that, their losses are low there. But in the case of a coaxial cable, that has a higher power loss. And then the waveguide can be operating from this three band. We say that 300 megahertz to 3 gigahertz. Okay, then 3 gigahertz to 30 gigahertz, then a 30 gigahertz to 300 gigahertz. That is, we can say that UHF band. Okay, then we can say that SHF band and a extremely high frequency band. Okay, ultra high frequency band, super high frequency band, extremely high frequency band. So that is about your we need to talk about this a rectangular waveguide. Now in the next lecture we will see that okay, that is about what are the various modes of the propagation. Now if you just see that the rectangular waveguide as compared to the coaxial waveguide, the coaxial cable, rectangular waveguide is better, and your signals are confined in the waveguide. That's why there are no losses, no interference, or power handling capability is again large as compared to the coaxial cable. So that is about a conclusion remark from this facts about this rectangular waveguide or waveguide there. Now, thank you all of you.